Hello and welcome to our 24th session. In today's session we'll be continuing our discussion of the BJT operation. We'll be looking at it a little bit more quantitatively. Specifically, we'll be looking at reverse active mode, and then we'll be looking at the general formulation. So the mathematics is going to be a little bit more involved than we've had in the last session. And finally, we'll wrap it up with a PNP BJT summary. And to get us started, I'd like to share with you a marvelous aria from Mozart's The Noche de Figaro, the Marriage of Figaro. And the aria is Non più dai farfallo amoroso. And it's a wonderful song to learn the lyrics. You can sing it in the shower and have a lot of fun with it. The problem is, for me at least, I sing it also outside of the shower, and that's not so good, because not for other people anyway. So you don't want to do that unless you're really a good singer. At the end of the aria, you'll see the conflict, the tension between the ruling and the servant classes, and that's what the Marriage of Figaro is all about. We'll be listening to Herman Pry as Figaro and as Susanna Mirel Freni, and we'll see you back in about 4 minutes.
Dio piccolo cherubino, come cangia in un punto il tuo vestito. Non ti entrai farfallone amoroso, notte e giorno di torno girando, nelle belle tormento al riposo, Narcisetto adocino d'amor. Nelle belle tormento al riposo, Narcisetto adocino d'amor. Non ti avrai questi bei pennacchini, quel cappello leggero e gallante, quella chioma, quell'aria brillante, quel vermiglio donnesco color, quel vermiglio donnesco color. Non ti avrai quei pennacchini, quel cappello, quella chioma, quell'aria brillante. Non ti andrai farfallone amoroso, notte e giorno di torno girando, delle belle turbando al riposo, Narcisetto adocino d'amor. Delle belle turbando al riposo, Narcisetto adocino d'amor. Tra guerrieri a farbacco, gran muscati stretto stacco, scoppia in spalla, scappa a fianco, colla dritto, muso franco, un gran casco, un gran turbante, molto onor, poco contante, poco contante, poco contante. Ed invece del fandango, una marcia per il fango, per montagne e per valloni, con le nevi e soglioni e il concerto di tromboni, di bombarde e di cannoni, che le palle in tutti i tuoni all'orecchio fan fischiar. E non ti avrai quei pennacchini, e non ti avrai quel cappello, e non ti avrai quella chioma, e non ti avrai quell'aria brillante. Non ti andrai farfallone amoroso, che notte e giorno d'intorno girando, delle belle trovando il riposo, Narcisetto adocino d'amor. Delle belle trovando il riposo, Narcisetto adocino d'amor. Che rubino alla vittoria, alla gloria militar, il rubin della vittoria, alla gloria militar, alla gloria militar.
Okay, so these are the topics we'll be covering today. We'll be basically doing the same thing we did last time, except we'll be a little bit more quantitative this time, and we'll be switching back between the NPN and the PNP, and we'll try to make it clear what the forward bias is on each of those as we go through them. Okay, so let's now start our more quantitative discussion, and here we're going to be looking at the NPN. So it's got an N emitter, P base, and of course a N collector, which is not shown, but we're interested right now in the emitter base junction right here. The depletion region on the emitter side is composed of positive N ions. The depletion region on the base side is composed of negative acceptor ions, so that the field goes from left to right. That's the first thing we need to remember, that if we have a depletion region on the N region, it has donors. Donors give up electrons and they become positive ions. So if the field is going from left to right, which is the positive direction, then forward bias, which is what we want to do, we want to bias the emitter base junction in the forward direction. The emitter side must be negative and base side must be positive, which is in opposition to the internal field. The external field goes from right to left. It's in the negative direction. Again, we can think about this as the negative electrode here pushes or repels electrons to cover up some of those positive ions, making the depletion region smaller. And of course, because we have an N emitter, we are injecting electrons into the P base, and that's exactly what this says. There's an excess of electrons which are injected from the emitter into the base, where they become minority electrons in the P base. Okay, and this delta here, the excess, is the number of electrons that are injected minus the equilibrium value of the electrons in the base. And of course that is the boost. That is this number right here. E to the VBE divided by KT, and this is the equilibrium number. So this is the first term is the new term, is the non-equilibrium term minus the equilibrium term, and that is the delta N sub P. And again, just to repeat, we are forward biasing the junction, which means that the barrier is lowered. It's like a two-way gate, so we have electrons pouring in this way from left to right, and we have holes pouring in the other way from right to left. The difference is there's a hell of a lot more electrons than there are holes, because we make the emitter degenerately doped 10 to the 19th, and the base is only moderately doped to 10 to the 17th, and that's exactly what we're saying here. A lot more electrons than there are holes, therefore the excess of electrons is much greater than the excess in holes. Other than that, the two equations for electron excess and hole excess look to be the same. The difference is in the equilibrium values here. And we put some numbers in. You can see that the equilibrium value of the electrons on the P side is 10 to the third, because it's doped 10 to the 17th. 10 to the 20 minus 10 to the 17th is 10 to the third. And the excess of holes in the emitter side, because there are only 10 of those, 10 to the 20th minus 10 to the 19th leaves us basically 10. So they're much less. That difference, the ratio of 100, is basically our beta. And again, we are interested in the diffusion current. So this is deja vu all over again. This is the minority carrier diffusion equation. We've derived it in an earlier chapter. We used it in the p-n junction, and we're going to use it again. The first term is 0 because it's steady state on the left, and we're not shining any light, so we have only the two middle terms, and that is equation 1441. Okay, so we have two cases. Before we get into the cases, I should again reiterate that tau sub b is the recombination time in the base. That is where we are interested in, and that is where the electrons, because it's NPN, potentially could recombine with holes. We could write the same equation in the emitter, but I don't really care what happens in the emitter. The emitter can go to hell. It's not important. The base is what's important. And I should again restate, and this is really a big deal, we cannot, using first principles, derive an expression for tau b. We have to be given tau b. So if you ever see a homework problem or an exam problem where they say calculate TB, you can put a little note on there. I found out your trick. You can't calculate TB. TB has to be given. That would be a rather trick question, rather nasty, something I might do. Okay, so we look at the long base. The long base is where we have a long emitter, and eventually the electrons are going to die out by diffusion, and we have an exponential. And going through this again, we can see that A2 must be 0 because the number of excess electrons doesn't increase, it must decrease. So we only have the first term here, and X is always much less than the neutral, quasi-neutral region in the base. We talk about a diffusion length, and again, we remember that the diffusion constant or diffusion coefficient has units of centimeter squared per second, so we multiply that by tau b, which is in seconds, take the square root, and we get a length. So A1, the boundary condition, is at x equals 0, so A1 is the excess electrons at 0. This is not equilibrium, this means at the point x equals 0, so we put that in. And here we have this solution. We find the current simply by differentiating, which brings down ln on the denominator. So if WB is 10 microns and L sub n is 1 micron, that's pretty extreme. Certainly the neutral, quasi-neutral base is much longer than the diffusion length. And here is an expression for the current density. We're just differentiating this and differentiating the solution. And we have a ln on the bottom. Okay, the second kind of quote-unquote special case is the short base, where the diffusion length is much greater than the quasi-neutral length in the base, and then, or the tau b is very, very big. Up here, where is it? Must be someplace. Yeah, so this term goes away. We have the second derivative is equal to 0. This is just like we did in the p-n junction. Of course, that's what it is. It's a p-n junction, or in this case, an NP junction. And here we get a linear expression. The first derivative is constant. The second, and then the integrated twice, and we get a constant. So now we have two constants of integration, which we have to figure out. But fortunately, we have two conditions. We know the excess minority carrier concentration at x equals 0. That's where we start. And in the base, not in the emitter, we start at x equals 0 in the base. and we know the excess carrier concentration at the end of the journey when it gets to the base collector junction. Now, in the, again, pretty much repetition, but good to review these things a couple of times. In the PN junction, this B would be 0. In our case, it is not 0, and that is really kind of important. It depends on the doping densities and the biases in the base collector junction. Two conditions here. We have the number of excess electrons. I probably should have put in a subscript P here, but you get the picture. I cannot do it. Sometimes I leave it out, a little bit sloppy, shame on me. But this is the excess electrons at the emitter base junction at x equals 0, and this is the number of excess electrons at the base collector junction. So we know these two numbers. This is a little bit more tricky. This went to 0 in a PN junction. Now it is not 0. If we have a high reverse bias, this can actually be under this number here. This would be the equilibrium number, and we can actually go below equilibrium, essentially making it 0, just like the PN junction. However, if we have a forward bias at the base collector junction, this number could go way, way up, and we could get almost a horizontal line, and that is the reverse, or the saturation mode, not the reverse active mode, the saturation mode. Okay. So we can write using the point slope method. It's just a line, no big deal. This is the one that varies with doping and, more importantly, with bias, reverse bias or forward bias at the base collector junction. And so that's what we've got there, pretty straightforward. Just the slope times x plus the constant b, which is from here. Okay, so we just used high school algebra there. And now we find that the current density, we just differentiate this, just bring down this constant, and of course this term goes away, and that is a expression for the current in a short base emitter base structure. And we could ask why the minus sign here. Well, electrons are going from left to right, which means that current is going from right to left. We don't have to worry about that. Just at the end, use a sanity check, and if it's holes going from left to right, this would be positive. If it's electrons going from left to right, it's negative. No big deal. J is constant in this case, independent of position, and it depends on the value of the forward bias at the emitter base junction and the value of reverse bias at the base collector junction. And again, repeat, if that is not reverse bias, if it's 0 bias, this would be the equilibrium number. If it is forward bias, this number can be high. In fact, it could be such that the whole numerator here goes to 0, and that is called the saturation mode. And here we get kind of a summary of those two conditions. Here, notice that in the emitter, generally this would not be the key. We would not have a straight line here. We could, but generally it would be a long base, and the current would die off. This is the long base condition in the base region, not desirable. This is the short base condition in the base region, which is desirable. And we have some examples. Now, if I was really nasty, I am, but I don't know, for some reason I became nice this time. I probably should have done this as PNP, which everything would be flipped. But we'll keep it as NPN. That's what we've been working on. And the question here, or the example here, we're going to calculate the collector current under the assumption that we have a short base. That's the good guy, and that makes sense because that's what generally we will have. We want to calculate the emitter efficiency. Of course, no recombination, that's why it's short base, which implies, of course, that the collector current is equal to the emitter current. Whatever comes into the base goes out the collector. And that's why we have the transport factor of 1 and no recombination. There is no charge injected from the collector into the base. That is a condition which we will relax a little bit later on when we look at the more general solution. And we're given the, in this case, the base neutral quasi-region and the emitter quasi-neutral region are both 0.5. That's a little bit, it's a little bit high for the base. In fact, it's quite high for the base. We might be thinking about bases which are somewhat less than that, like 0.2, 0.3 micron, and it's really quite low for the emitter. For the emitter, we might think about 2 or 3 or 4 microns. So, for the purpose of an example, we'll take it as both equal and at 0.5, and the cross-sectional area is 4 times 10 to the minus 4th, because we'll be looking at currents rather than current densities, and that's about 200 microns by 200 microns, and that's a pretty reasonable number. We have our standard dopings, 10 to the 19th for the emitter, and it's N, that's why it's ND. For the base, 10 to the 17th, so there's a factor of 100 between the emitter and the base, and for the collector, lightly doped at 10 to the 15th. Okay, now here are the junction voltages. We're going to start off with no bias at the base collector junction, and we'll be looking at biases of 0.5, 0.6, 0.7, and 0.8. 0.8 is probably about as high as we would want to go for a forward bias at the emitter base junction. And then we're going to repeat the calculations for the base collector junction voltage or bias, reverse, a little bit of reverse, a lot of reverse, and then plus, which means that it's going to be forward biased. The last value reverses the normal bias. This would be the normal bias. Very nasty of me. This 0.4 is not reverse bias, but it reverses these two guys, and it actually becomes a forward bias. And then we'll plot those curves. Okay, so the only other thing we need here is the mobility. Why do we need the mobility? Well, because we need the diffusion constant. I never could tell if it's diffusion constant or diffusion coefficient. It's not that it matters, but from the Einstein relation, D over mu is KT over Q. KT over Q is a constant, so as the mobility goes down, the diffusion constant goes down. Not a good thing. In this particular case, because it is an NPN, we have the mobility of electrons, which is always higher than the mobility of holes. So I think 750 is a reasonably good number for the diffusion constant in the base. So we start with the excess electron concentrations NP at the base side, the start, the interface between the depletion region and the neutral region in the base. So that's 0. And if we look at first a forward bias of 0.5 volts, 0.6 volts, 0.7 volts, 0.8 volts, we get 2.2 times 10 to the minus 11th for the lowest voltage, and then it goes up, way up from there. The 0.6 volts is actually rather something rather interesting. We can do that in our heads, hopefully, because we know that 60 millivolts, 0.06 volts, should give a factor of 10. 60 millivolts per decade. So 60 millivolts times 10 is 0.6 volts, so it gives 10 decades, or 10 to the 10th. 10 to the 10th times 10 to the 3rd, which is the equilibrium value, is 10 to the 13th, and we can see that for the just an increase of 100 millivolts, a very small increase in the forward bias, we get over an order of magnitude in the excess electron concentration. So that's what I'm saying here. We start with the equilibrium concentration of 10 to the 3rd, and we put in 0.5 divided by 0.026, and we get 2.2 times 10 to the 11th, and the others are done just the same way. Okay, so at the other end, at the base collector junction, we have relatively small value. Now, if it was at a PN junction, this would be precisely 0. Here we control this number by putting a bias at the base collector junction. If we put no bias, a 0 bias, of course 10 to the 11th and 10 to the 3rd, it's just 10 to the 11th. And we get a current density, putting in the numbers Q, dN of 20 is the diffusion constant for diffusion coefficient for electrons in P media. The N denotes that it's for electrons. Put in the value at 0, and of course this is basically 0 divided by the neutral base width, which is a half a micron, and we get 1.4 times 10 to the minus 2 amps per centimeter squared. It doesn't mean very much right now, but let's take a look at the others, and they go from 10 to the minus 2 to 10 to the 3rd. That is a 5 orders of magnitude jump, even though our forward bias is only increased by 300 millivolts. And that, folks, is the power of exponentials. And if we want to find those in amperes, it's pretty straightforward. We just multiply by the cross-sectional area. So these are the numbers we would actually measure on an ammeter. It goes from microamps to amps. So when we put a forward bias of 800 millivolts, we're really smoking. That's 0.6 amps. That's hot stuff. Okay. Now, if we increase the reverse bias, I mean increase in magnitude, so that it's from 0 to 0.6 volts, that's 0.6 volts reverse bias, we basically get 0. Well, does it change anything? No. It was already essentially 0. 10 to the 3rd and 10 to the and 0 it's the same thing, because we're comparing it with 10 to the 11th plus. And even if we go to let's see, if we increase the bias to, here it is, to 0.4 volts, this should be reverse bias. If we increase the reverse bias to 0.4 volts, then we get 10 to the 9th, which is still essentially 0. So let me correct that right here. This is reverse bias. Reverse bias, 0.4 volts. So really, under the present conditions, it doesn't matter what the bias on the base collector junction is. If we have a very low bias, however, on the emitter base junction, and we have a higher voltage of, say, 0.6, 0.7 volts at the base collector junction, reverse bias, then it starts to matter. And so to calculate the beta, well, we did the electrons going from the emitter to the base and into the collector. That was pretty straightforward, I hope. And now, to calculate the beta, we have to look at the holes that are injected from the base into the emitter. That's the input. The output is the holes that are the electrons that reach the collector. That's the one we did previously. Now we look at the holes, and we start out not with 10 to the third, but with 10, a much, much lower number, 2 orders of magnitude. And we would expect, exactly as we would expect, that all of these numbers are 2 orders of magnitude less than the numbers here. Where are they? Must be someplace. Ah, here they are. 10 to the 11th, 13, 14, 16. I can remember that. 10 to the 9th, 11, 12, 14. So these essentially are 2 orders of magnitude less than the electrons which are collected. And that gives us a beta of 100, exactly as we would have expected. And those results are summarized here. And very briefly, let's take a look at the reverse active mode. My argument in the reverse active mode is like this here. Well, obviously we know what the reverse active mode is. It is a situation where we reverse bias the emitter base junction and forward bias the base collector junction. Okay, so I'm making an argument here that the base current is what has changed, and the voltage VCE between the collector and emitter has essentially reversed in sign, and since electrons are flowing from the collector to the emitter now, because the collector base is forward biased, so we have electrons flowing from collector to emitter, the current is in the opposite direction. The base doping, of course, hasn't changed. It's just 10 to the 17th, so what it was in the forward active. That is a structural issue, not a biasing issue. In the forward active mode, the input current was the base current flowing from base to emitter. But here the base current has changed dramatically. There is a large base current which can flow from the base to the collector. There is very little current flowing from the collector to the base, but there's a large amount of current, in this case holes, flowing from the base to collector. And we can see that by these numbers. These are holes that are now flowing from the base starting at 0 and collected by the collector. And you can see how large those numbers are for forward bias, not at the emitter base junction, but at the base collector junction. And because we have a large input current, that's this thing right here, that's the input side, the base to common emitter, the base to emitter voltage, or base to emitter current is the input current, and a very small output current, yikes, the beta is essentially 0. Okay, and that is shown here. This is the forward active mode, which we've been dealing with, and in the reverse active mode, we have holes, and we can see that the beta, well, actually we can't see it from this diagram, but we can see it from these numbers that the beta we would expect to be essentially 0. This should not be log delta px. This should be basically, and I'm going to just correct, it's just log value. So let me take that out. Okay. Log of excess current, whatever, or excess charge, whatever the excess charge is, electrons or holes. Okay. Now example 3 is basically what we've been doing. It leads into the general formulation, and I'd like to skip over right now, at least take a stab at the general formulation right here. We're looking really at 6 components, and let's just take them apart. One, that's the one we always have. We're going to forward bias the emitter base junction. We've got holes which are injected from the emitter into the base, collected by the collector. There may be some diminution in the number of holes because we're going to assume the most general condition. Forward bias on the base emitter base, reverse bias on the base collector. 5 and 6, notice they go in opposite directions. These are electrons which can be injected into the emitter from the base, or they can, at least in theory, be injected from the base into the collector. This guy is the important one because this is the input current which controls the output current. This one is not important, that's why I made it smaller. And the reason is this is electrons, consists of electrons which are injected from the base into the collector, but at the terminal here for a generally a good operating mode, even in saturation mode, we would have this generally as a minus sign here. So if we have a negative voltage at the collector terminal, it would repel these electrons. So number 6 is essentially 0. We don't have to worry about it. And of course number 3 is very important in the reverse active mode, can be important also in the saturation mode if we have a small forward bias at the emitter base junction and a large forward bias, also forward bias, at the base collector junction. I can get a reasonably large current consisting of holes which go from the collector into the emitter. So, at least in theory, in saturation mode, 1 and 4 could be equal. And that's when we started out in our last session, where we had symmetric doping and symmetric biases, and we found that there was a clash, 1 and 3, a clash of currents, and they basically canceled one another out, and that's called the saturation mode. So you can just reiterate all these things, and 6 is least and last, both. Okay, so now we start to analyze this crazy thing. We start with component 5, for example, which is here. That's an important one. That's electrons that are emitted from the base into the emitter, and we get a EN current. We've seen that before a number of times. Component 6 basically is 0 because VCB or BBC, it doesn't matter. It's a reverse bias. So this term is very small and it's essentially non-existent. Okay. So going back to component 1, that's a big one. That is the for PNP, that's holes injected from the emitter to the base, and that's a big deal. Here it sits, and we begin by writing the minority carrier diffusion equation in steady state, only at the base. That's the base is the important thing. But now we're not going to assume that tau goes to infinity. And here we have the base. The neutral base region is WB. And we have the general solution for this differential equation, which is an exponential. And it has 2 terms. We've seen this before. It's going to be a little bit more interesting this time around than we saw for the PN junction. Okay, so we have the excess carrier concentrations at the emitter base junction and at the base collector junction, which allows us to solve for the 2 constants, C1 and C2, and these are now become known constants. They're not. That's not the A1 and A2. A1 and A2 we have to find in terms of C1 and C2. C1 and C2 are just numbers that were given. They're numbers due to the biasing and due to the structure. So I'm not going to go through this in detail, but if you go through the equations at the boundaries, you'll find that A1 plus A2 is C. That is x equals 0. For example, we substitute x equals 0. Where is it? It must be someplace here. Here it is, x equals 0. We have A1 plus A2, and that is equal to delta PBB at 0, but delta PBB at 0 is given by this thing, which is called C1, and the same thing for C2. So now we have C1 and C2 in terms of A1 and A2. So basically all we do now is we solve for A1 and A2. Two equations, two unknowns, solve it. So we turn the crank. It's not particularly pleasant, but we eventually wind up with, I believe it's 1488. And this is it right here. 1488 is the general expression for the excess carrier concentration as a function of x. This is a function. Where's the x here? Right here. Where's the x? And as expected, it's a combination of cinches. When we differentiate it, we're going to get Cauchys. There are two terms, unlike the last time we did this at PN junction. We didn't have a VCB. We had no base collector junction because there was no base collector. So this term is new right here. This term is new in the BJT, which we did not have in the PN junction. So we can now find the current from the emitter, and it's consisting of holes. And here it is. Again, it is a function because there are x's. Here it's not a constant as it was when we had the short base. It is a function. Okay. At x equals 0, if you put in x equals 0 here, this becomes 1, and this becomes cosh omega b over sinh omega b, and the whole thing at 1488 at x equals 0, 1488, the excess carrier concentration collapses. Now let's see why that's true. The sinh of 0 is 0, so this whole term goes away, as we would expect. And the sinh of omega b over lb, sinh omega b over lb, this goes to 1. So all of it, this whole term collapses to bp0 e to the qeb divided by kt minus 1. And that's what we see right here. And at w equals xb, we have something similar. W equals xb, oh, where it is, okay, W equals xb. This term collapses, and this term goes to 1, WB over LB, WB over LB. So this term goes to 1, this term goes to 0 because we have sinh of 0 on top, and we get the last term, exactly as we would have hoped and prayed. So that's a good thing. That gives us some confidence that 1488 is correct, and if 1488 is correct, the derivative is certainly correct, because the derivative of this guy is pretty straightforward. There's only one term we have to differentiate. The sinh goes to cosh because the derivative of the sinh is the cosh, and we have two coshes instead of two cinches. So that's a sinh. Excuse the pun. Okay. Discussion. Why do we have exponentials in the first place rather than sinusoids? Well, if we have sinusoids, this thing would be going up and down and up and down and up and down. And actually, it goes back from a mathematical standpoint. It's pretty straightforward. We would have had sines and cosines if this was a plus here, because the way that the differential equation is structured, if this were a plus sign rather than a minus sign, the solution would be sines and cosines. If it's a minus sign, it's cinches and coshes. Of course, cinches and coshes are kissing cousins. They're very close one to the other. So we shouldn't be, once we know sines, we know cinches, and vice versa. It's just a matter of the square root of 1, square root of minus 1 in the exponent. So that's pretty straightforward. And I think we can skip over because we're just running out of time here. This is fairly straightforward, this diagram, this table here. That's just a summary of what we've been talking about. This is for PNP. For an NPN, just wherever we see N, you put in P, and it's pretty much the same thing. Okay, so we'll end with a video clip. And I didn't put in the video clip. So, oh, we're going to end. Well, it's a surprise. Okay, so this is the video clip that we're going to listen to now is also from the Noche de Figaro, the Marriage of Figaro by Mozart. The aria is Dove Sono. It's considered one of the most beautiful songs ever written. It is sung by Tiri Te Koana, I should say Dame Tiri Te Koana, from New Zealand, marvelous soprano of the late 20th century. Her mother is European, her father is Aborigine. She's a beautiful woman, and she has an absolutely magnificent voice. So let's enjoy Dove Sono, and we'll see you next time.